See, what is traffic engineering? Any idea? What do you think is traffic engineering? In networking, traffic engineering means we allow the traffic to go as per the policy. So what you did in BGP is a traffic engineering. What you do in quality of service is a traffic engineering. You want traffic to go in some special path, special reservation you want to give. All these are traffic engineering. Here also we see a traffic engineering, but this is not QoS traffic engineering. This is not BGP policy traffic engineering. This is using MPLS with labels. You are going to provide some policy-based routing using labels. See, those quality of service that you learned earlier, the BGP, all those things are IP, not label-based. This traffic engineering is using MPLS label. Now, see the first 3 points that which you already read in the screen. Very nice points. Why MPLS traffic engineering is needed? The very first point is the most important point. IGP limitation, OSPF limitation, ISIS limitation. What is the limitation of this? So far you might have not realized that it's a limitation. What it is? Using the shortest path only. You might have celebrated this actually for this many years. You might have celebrated OSPF, shortest path first. ISIS, low cost path. You celebrated it. But here we see it's not something to be celebrated. It is a limitation of routing protocol. It's a limitation of routing protocol. OSPF or ISIS forwarded traffic based on shortest path only. Why it is limitation? See, if you have multiple paths and you are using only one path for all destination, even when the link is fully congested, you are not utilizing any other path. You use only the shortest path. That's the problem. That's the problem. You have multiple paths. But you say, I use the low cost path. For all destination, my routing table is going to show only one path. Though there are multiple paths to reach the destination, you're going to send through one path. All will use that one path alone to the destination. From wherever it may come, it is going to use, again I repeat, from wherever it may come, you will use only that one path to that destination. So, from anywhere traffic comes to the destination, you have only one path. And if there is too much of traffic coming from various source to that destination, that one path will be a congested path. But you have no other option, no other choice to make, because routing protocols only use the best path. You don't have any other option. Though there are other paths, it's not utilized. It remains underutilized. It remains underutilized. I've seen in some families, they don't allow children to grow. They don't allow children to grow. When they go for a vacation, I'm blessed with a big Jeep. So Jeep is inside my compound only. We load everything in that. Otherwise, husband only would have carried all the load on the head and the shoulder. Not everyone is blessed with Jeep. So they don't allow children to carry any luggage. Only the man of the house should carry everything. Poor guy. They could have shared the load with everyone. All have got two hands. Likewise. என்ன அன்பு அப்படிதானா? That's how we see in India. ஆமாவா? சூப்பர் பாருங்க என்ன மாதிரி frequency. So there's a limitation of this IGB protocol. What is that? The entire load will be kept on that one shortest low-cost path link only. All other links are underutilized. With a traffic engineering, you can make use of all the paths. With a traffic engineering, so traffic engineering is something like a clever husband who smartly deals with the family to load balance, not carrying everything on his shoulder, on his head. Some smart guys, they're really smart. They know how to manage, talk, deal with things like this. Clever boys. That is traffic engineering. Okay, fine. The elder son will carry this bag. It's full of cloth only, not too heavy. The next one will carry all the water bottles. We are all going for an excursion, vacation. All should work together, all should carry together, all should enjoy together. All enjoyment part only they will take, and this man, poor man, will have to bear everything, including petrol, booking hotels, restaurant, everything this man only should do. That's like OSPF and ISIS. But traffic engineering is like planning everything ahead. Okay, we will have this much of luggage. We don't have a car. We need to take train and bus, and then we go to Kanyakumari. We go to Ooty, Kodaikanal. Then how we are going to carry the load? That is also included in planning for a vacation. That is what traffic engineering in here, MPLS, RSVP, traffic engineering do. Only OSPF, only ISS. No. It's a routing protocol. Good, it finds one best path and gives. But don't rely only on that. We all should load balance. Only then it can become a nice, happy network, like happy family. Traffic engineering is that. Making use of all other links, not just the short path link, all links. MPLS traffic engineering is needed for this. Utilization of all available links. When I was a small boy, I remember I was in 5th standard, my sister was in 4th standard. My father put me in a government bus in Chengalpattu. Only me and my sister. Government bus, public bus. Nowadays no parents will do that one. and I came to Tiruvannamalai. We both alone, me and my sister. We took another bus to my native Tirupattur. That's another government bus. How old am I? Maybe 10 years old. Traveling for 350 kilometers alone. Me and my sister. So that made me a man. But nowadays people don't allow their children to become a man. Pampering, even during college, they will say, Kanne. Then he will never urubdify. Urubdame poirva. Kanne, kannana. Traffic engineering goal. Optimize bandwidth usage by steering traffic through non-shortest path when required. See, very nice. Whenever that one primary path is fully congested, that is what it means when required, whenever needed. Whenever needed. When it is needed, when that one shortest path is fully congested, you steer the traffic through non-shortest path. You're steering it. You're driving the traffic through the route which is not even there in the routing table. That's the point. I'm going to make it very clear. You don't have the route in the routing table. You have only the shortest path in the routing table. MPLS using RSVP traffic engineering can even use those routes to the destination which are only in the database, OSPF database, ISIS database. Yeah, it can even use the route that is there in the database. It can steer the traffic through the non-shortest path. Non-shortest paths will never be seen in the routing table. Correct, no? Only the best path will be seen in the routing table. Here the packets are steered through a non-shortest path first. Next, predictable traffic flow. Now, when you are sending all the traffic via one single path, even though you got multiple paths, when you send only through a shortest path, congestion happens. You cannot predict the delay. You cannot predict the time taken for the traffic flow. But when you are able to steer the traffic through the path which is not there in the routing table, you can avoid congestion. So everywhere you can easily have a predictable traffic flow. You understand? So RSVP traffic engineering allows to determine the path selection through selection rather than the best path forwarding. So not only in the shortest path you forward the traffic, you also steer the traffic through a shortest path. That helps us to achieve a predictable traffic flow. Because you are able to use all the available paths, you will be now able to predict that there won't be a congestion in my network. Okay. Point number 4. QoS aware routing. Yes, through MPLS RSVP traffic engineering, you can tell even this what? Give me a path which has got this much of bandwidth for the traffic coming from X going to Y. I repeat, there is a customer X. For that customer, you have given a bandwidth. You have given a bandwidth for the customer. You have given a bandwidth, and you need to guarantee that that customer always gets that bandwidth. In any circumstances, the customer should be provided that bandwidth. So you can configure traffic engineering in such a way that before sending the traffic of that customer, this MPLS traffic engineering using RSVP will check the path. Is this path having that bandwidth? If it is not having, then find the path which has got that bandwidth that's supposed to be given to that customer, and reserve the path for the customer. Provide the new labels for the new path and use the path. Once the customer finish using, then remove the path. As long as the customer is using, the path will exist. So what I'm trying to say is, MPLS traffic engineering using RSVP can dynamically, during the runtime, check the availability of the bandwidth that is committed to the customer. If available, it will allow the traffic. If not, it will find a path. It may not be there in the routing table. It dynamically finds the path from the database, dynamically finds the path, and dynamically reserves the path, and dynamically provides the label for the new path, because MPLS, no, it needs label. Now you are going to use another path. Where is the label for that? That is also dynamically generated during the runtime and distributed using RSVP itself. For this, we need MPLS traffic engineering. QoS aware routing. Carrier grade requirement. ISP needs strict control over traffic placement for service level agreement and premium service, which I just said, QoS aware routing. See, these ISPs need a strict control over the traffic placement. In which link I am placing the traffic? Is the link suitable for this customer, for this constraint that I have given for the customer, for this constraint, for this premium service? Is this link eligible? It will check. Only if it is eligible, it places the traffic. Carrier grade requirement. 5 wonderful points why I need traffic engineering to overcome the limitation of IGP. For traffic engineering goals, for predictable traffic flow, for QoS aware routing, for carrier grade requirement. Any question on these 5 points? RSVP traffic engineering fundamentals. RSVP TE definition. RSVP means resource reservation protocol is extended to signal MPLS label switch path with bandwidth reservation. That's the story. That's the complete story of what RSVP TE means. See the title itself, RSVP TE definition. What is RSVP TE? RSVP is extended. This protocol is extended to signal a new path with a label. The path with the bandwidth that is needed for customer X. Customer X, for all his traffic, you have promised 300 megabits. This RSVP can signal that path which has got that 300 meg with the label. Hey, this path is the best path for this customer. Here are the labels that we will use in the path. Push label, swap label, and pop label. So that the router will start using this path, which is well suitable for the customer. That path may not be the path in the routing table. The path in the routing table everyone is using. So it is fully congested already. You don't have that bandwidth 300 meg. That's why RSVP, what it does, it picks another path which is not there in the routing table, but which can take you to that destination. How it does? It signals the label switched path with the labels for all the routers in the path, so that using the label, traffic can come now through this alternate path provided by RSVP. So this is a signaling protocol. It signals saying this path is suitable. RSVP is a signaling protocol. Based on the constraint that you say, you are saying for this customer I need 300 meg. That's the constraint. RSVP will find the path and signal. Again, the path should be there. It's not a routing protocol. It is using the routing information that is there given by your IGP protocol like OSPF or ISIS, finds the best path for this customer and signals it. So RSVP is a signaling protocol. Now, one more thing is very important. We need to do both the side, because RSVP is a unidirectional. What does that mean? So this is the primary path. Everyone from alpha go to beta only using the primary path. Not only from alpha, everyone from A goes to beta via the primary path. Even from Ka, everyone goes via the primary path. Everyone from A also goes via the same primary path. No one is using the below path. But there is a customer here called Epsilon who wants to have a path with a reservation of 400 meg. He also wants to go to beta, but the path given to Epsilon need to have 400 meg. Anywhere you check here, it should have 400 meg. Everywhere in the path 400 meg is mandate. If it is not there, no, I don't want the path. Not even one bit less than 400 meg. It needs that 400 meg path. Because everyone is using Ka is using, Alpha is using, everyone is using this path only. There is no 400 meg now. So what RSVP does? It is checking this path. It's not having 400 meg. So it says no. It checks this path. 400 meg is available. So it reserves the path and gives this guy signal. From here it is signaling. From here it is signaling that guy. Hello, you can send via this path. Come via this path. Use this label. I give you the label. Leave the label. Distributes the label. Come via this path. It signals. So epsilon to go to beta, it goes this way. But return traffic, not guaranteed. It may come this way also. Why? It is unidirectional. So you should configure RSVP traffic engineering here also if you want this to go back on the same path. If you want both the request and the reply, the request is going from epsilon to beta. And you want the beta to go, epsilon also to go via the same path, then you need to configure RSVP even here. Because RSVP is unidirectional. Did you understand unidirectional? Yes. Very important point to be known. RSVP tunnels, if you are creating, you need to create not just one direction, both direction. For both to and fro. Right. Next point. Soft state protocol. RSVP periodically refresh state. Loss of refresh tears down the LSPs, meaning once the traffic passed through the newly derived path to match the requirement, see 400 meg is needed. So it didn't take the primary path, it took another path. But that path will not be there forever. It will refresh. It will check whether that path is still being used. If not, it will tear down so that someone else's traffic can be placed. So this is a temporary labeled switch path. Don't think that labels will be forever. Don't think that path will be forever. The path given by the routing table will be there. But this path, which is runtime decided, the path that matches the constraint, the newly established path with the help of RSVP will be teared down once the traffic finishes using the new path. Once the customer finish using the path, it will be teared down. We can also explicitly tell the RSVP that if customer is China, use this path. If the customer is Hong Kong, they are not same. China and Hong Kong are not same. If the customer is Hong Kong, then use the another path, that path. You can explicitly create the path from the head to the end, from the PE to PE, provider edge to provider edge 1 to provider edge 2. Provider edge 1 is head end and provider edge 2 is tail end. So we can decide the path. Explicitly you can tell. If China is coming, give this path A. If Hong Kong is coming, give path B. Explicit path creation. RSVP supports this. All right. So for those paths, label will be given by RSVP distributed. And that path again, it will be teared down once China finish transferring the data. Once Hong Kong finish transferring the data. You can explicitly create and keep it ready. As soon as China traffic is identified, it will take that explicit path that you said to use. You can have multiple paths explicitly and say, this is my first option. If this path is good, I prefer this. If not, this is my second option. Check this path. If this path has got that bandwidth, use that path. If that is also not having that bandwidth, you can dynamically decide. We can say that. So we have plenty of options in RSVP-TE. Any question? Did you understand what is RSVP-TE doing? First, we saw the need of traffic engineering. Now we are seeing RSVP-TE fundamentals. Now let's move on. The control plane. As I said earlier, RSVP is not a routing protocol. It is not a routing protocol. Which means without route in the routing table, RSVP cannot work. RSVP depends on an IGP protocol. EIGRP? No. RIP? No. Static route? No. OSPF or ISIs. So you need IGP and that IGP should be a link state routing protocol. OSPF and ISIs are the options we have. So this OSPF, opaque LSA, you might have seen. LSA type 9 to 11. That is what used. So RSVP will use OSPF database for traffic engineering. It copies the OSPF database and creates a new database for traffic engineering so that if the shortest path is not meeting the constraint, it can pick the alternate paths. So the control plane components is the routing protocol. Control plane means what? The one which shows the path for the traffic to be steered. Control plane example. Purushavakam Sellum Vadi left. Nungambakam Sellum Vadi right. Paris Sellum Vadi straight. That board you have on the main road. That green color board with white color writings, I believe. That is control plane. Then what is data plane? If you are sitting in an auto, you are the data plane. Your auto is the data plane. If you are sitting in a bus is the data plane. So according to the destination that you want to go, based on that signboard or the board that shows the direction to Purushavakam, Nungambakam, and Paris corner, you start driving your vehicle towards that direction. So here, which one is the control plane? IGP, OSPF, ISIs. Secondly, that OSPF database is not straight away used. It is copied. And each router builds a traffic engineering database. That is the control plane. In that traffic engineering database, not OSPF database, traffic engineering database, this particular algorithm, you know what? SPF, shortest path first. C is constrained, shortest path. What is constrained? 400 meg I want. You said no, I want 400 meg. That is the constraint. For that constraint, which one is the best path? Which are all the paths that has got 400 meg? In that 400 meg, in those paths, which one is the shortest? So CSPF, constraint based shortest path first, is what operates and provides the path. This CSPF contributes to the control plane. So head end router means what? First router, the PE1 router. PE2 is the tail end router. In between, you got many paths. Now, constraint based shortest path first is checking. Is this path having 400 meg? Is this path having 400? Okay, they are both having 400 meg. They satisfy. Now, in this, which one is the shortest? Okay, this is the, then let me use this one. That's the job of this constraint-based shortest path first. Head-end router computes the path satisfying the bandwidth and the constraints. Head-end router is nothing but the increase router. Traffic is coming from the customer. This is the increase router. Tail-end router is the egress router. This is where it goes out. This is tail-end router. Head-end router, tail-end router. So these are the components of MPLS, RSVP, traffic engineering, IGP, TED, CSPF, head-end router, tail-end router. Any question on control component, control plane component? Okay. RSVP signaling process. See, RSVP will signal when a path meets the constraint. When a path is discovered, it will signal. See, first what does it do? It sends a path message. From where? From head end. Via all available path, it is sending path message. What is path message? Asking, hey, do you have that 400 meg or not? This PE1 is asking this guy. It is sending a path message. Do you have that bandwidth? It says yes. Yes means it will forward to the next guy. Do you have the bandwidth? This guy says yes, means it will send to the next guy. Now let's say this is the tail end. And this guy will reply saying, reserve message. It is sending to the upstream. This was sent to a downstream. This is downstream. Now the reserve message is coming because in the path you have successful 400 meg. So this is sending a reserve message. Yes, I have. Reserve this path, reserve this path, reserve this path. and assign the label for this path. If this path is not the path which is there in the routing table, if it is new path, then it will populate the labels. Right. So each hop assigns a local label and builds its label switched path. Okay. Next, bandwidth reservation. Each links check the available resource bandwidth before accepting the label switch path. They check whether that bandwidth is available and then accept the labels for this new path. State maintenance. RSVP refresh message maintains the LSP label switch path state across the network. So as long as the bandwidth is available, that path will be there. If congestion happens in the middle, then it goes and finds another path. That is called reroute. Rerouting will happen because it maintains the state. It knows whether still that 400 meg is available or something made the bandwidth go less than that. If it finds going less than that, in the runtime only it will change another path. We call it as reroute. So RSVP signaling process is path message, reserve message. Path message goes from head end to tail end. Reserve message comes from tail end to the head end. Labels are allocated by each router and distributed. When the LSP label switch path is finalized, every router will check for the reserved bandwidth. If available, it finalizes. And state is maintained. It keeps checking. The refresh message maintains the LSP state across the network. Any question on RSVP signaling process? Do you have any question on RSVP signaling process? These 2 points are very important, path message and reserve message. Did you get these 2 points at least? You should know all points, but the 2 points are very important. Clear? Did you ask any question or you said yes?
Yes, sir.
Okay. Now, explicit path and constraints. We can specify a particular path for a customer. And that path that you specify is what called as explicit path. And this explicit path can be a strict path or it can be a loose path. What is strict path and loose path? Let's say you have PE1 and PE2 and you have 2 paths. I'll call this as A, B, C, D, E. Now, I want to write an explicit path saying from PE1 you go to D. And from D you go to PE2. This is the path I am telling. Whenever traffic comes from one particular customer, I am telling use this explicit path. See, this is what called as loose path. I am saying from here you go to D, which means it can take this path or it may take this path or it may take this path. I'm not worried about it. My aim is it should go via DA. I'm not specifying every hop. If you say exact next hop that the traffic should pass through, we call it a strict hop or strict path, strict explicit path. Loose explicit path is what I have written. I said from here, you need to go here, and from there, you need to go here. I'm not worried whether it goes like this or goes like this or goes like this. I'm saying from D you can go to PE2. I'm not strict mentioning every hop. I say go from here to here and here to here. In the middle you may have multiple paths. You can choose your own. I'm giving freedom for the middle routers. That is loose explicit path. See, intermediate hops are flexible. Strict hop, loose hop. Strict explicit path, loose explicit path. Bandwidth constraint. This is another explicit path. You are saying, I want a path with at least this much of bandwidth. 400 meg minimum. That is bandwidth constraint. Next, administrative constraint. I like, that is administrative. Affinity. I want my packet to go this way. I want this particular path. I want to include these links. I want to include this link while going from this to this. I want to include this link. So traffic, if it goes to C, then it will take this way. If it goes to A, then it will take this path. It won't come down. If it goes this way, it won't come down like this and go here. It won't come down because you said எனக்கு இது ரொம்ப இஷ்டம் in the link affinity. So if it goes here, it only takes this path. That is called administrative constraint. Affinity. To include or exclude some links. Any question?
Yes, sir.
Right. So very important point to be noted here is that strict and loose. Next. Tunnel behavior and protection. Tunnel priorities. Set up and hold priorities. Control preemption between tunnels. Yes. You can have multiple tunnels with different constraint and say if customer A comes, first preference give to tunnel 1. If tunnel 1 didn't satisfy, then go to second, then go to third. That preemption between tunnels. You can set priorities between the tunnels. So if that priority 1, that small number is highly preferred, when you configure, you'll be setting priority. Small number is always preferred. And if that smallest number priority configured tunnel, doesn't meet the constraint, don't have that enough bandwidth, then it will go to next one. That's tunnel priority. Preemption, higher priority tunnels can tear down a lower priority tunnel. Higher priority tunnel can tear down a lower priority tunnel. So when the higher priority tunnel is in use, lower priority no need to use. Fast reroute. Local protection using link and node protection backup tunnel. Say during the runtime, if there is a delay less than 50 milliseconds, you can say take another route, reroute. That's called fast reroute. See, it was nice when the traffic started sending, but during the flow, slowly the delay started. So you can configure FRR, means fast reroute, saying if you find delay more than 50 milliseconds, you have to take this path instead of the usual, instead of the normal. You can do that optionally. Again, it's not mandate, optional. Fast reroute is optional. Make before break. Allows path re-optimize without traffic loss. So make before break. So one path you are going, all of a sudden something went wrong, congestion happens. Immediately it will establish another path, it will find another path, and then only it will break this path. It will find another path, learn the labels for the new path, and flow the traffic through the new path, and then break the old path. Make before break. Re-optimization. Periodic recalculation for better path based on current network status. So during the runtime, it will be keeping an eye on the constraint requirement. If it is changing, if it is not matching, it will take another path. So it keeps an eye on the current network state. If the network state changes, then re-optimization also happens. That's why we call it as protection. Your data will not suffer. You get that guaranteed bandwidth. Even if it is rerouting, your packets are not going to be lost because it is going to be MBB, make before break. Yeah. All right. So this is what RSVP traffic engineering means. What is next? We need to see how to configure. With an example we will see in our next class. Any question?